Today we shall see about the equivalence of context free grammars with push down automata. When we say push down automata, we really mean non-deterministic push down automata. The equivalence can be shown only between context free languages and non-deterministic push down automata. So, we have to prove in two directions. Given a context free grammar, how you can construct an equivalent push down automaton, and given a push down automaton, how you construct an equivalent context free grammar. So, first we shall consider in one way, that is, let L be generated by a CFG G then L can be accepted by a PDA M by empty store. The equivalence we prove in this manner, that is, we show the equivalence between context free grammars and PDA accepting by empty store if the context free grammar is given, how to construct the push down automata accepting by empty store, and if push down automata accepting by empty store is given, then how to generate the context free grammar. This way we will prove. We have already proved the equivalence between PDA accepting by final state both directions we have proved. So, that means given a CFG you can construct a PDA accepting it by final state, and given a PDA by final state you can generate the context free grammar. That is also possible, as this is transitive, equivalence is transitive. So, you can prove that way. So, what we consider today is this: given a context free grammar, how to construct the push down automata which will accept the language generated by the context free grammar by empty store. Actually, two proofs are possible. In one, you can assume that the context free grammar is in Greibach normal form. In another proof, no such assumption is necessary. So, we will take the proof where there is no assumption first, and then how the proof is given for the case when the grammar is in Greibach normal form we will take up later. So, here you are given the context free grammar G is equal to NTPS. Now, you have to construct the push down automata M is equal to K sigma delta etc., but K is just only one state, you can do it with one state. K sigma is T, gamma is N union T, all symbols which are non-terminals and terminals can be stack symbols. Delta you have to define, Q naught, there is only one state, that has to be the initial state, and the initial start symbol is the initial push down symbol, and because it is acceptance by empty store you have phi, right. So, you have only one state, you can accept with one state, and the terminal symbols are the input symbols, the stack symbols or the push down symbols are N union T, delta we have to define. There is only one state, it has to be the state throughout, does not make any difference. The initial push down symbol is the start symbol of the grammar. No final states are specified because it is acceptance by empty store. Now, we have to define only delta. Delta is defined like this: if A goes to beta is in P, the context free rules are of the form, the left hand side you have a single non terminal, On the right hand side you have a string. What is B? Beta belongs to n union T star. It is a string of non-terminals and terminals on the right hand side. If this is a rule, then you have delta of Q epsilon A contains Q beta. You make an epsilon move, you do not read any input, but on the push down stack you replace A by beta. Please remember that when we write like this, the leftmost symbol of beta becomes the top of the stack. Then for each A in T, each terminal symbol you have delta of QAA contains Q epsilon. This is all the mapping, delta mapping you have. Now what we have to show is LG is equal to N of M. This is what we have to show. Right? Construction is this, grammar is given, you are constructing the push down automata like this, then you have to show this. This proof is of course by induction, we will go to that in a moment. Before that, let us illustrate the construction by an example. Let us take the familiar example you have. G consists of two rules. Then you have the push down automaton, M is equal to Q, input symbols are A, B, push down symbols are A, B and S, initial state is delta we have to specify, initial state is Q, initial push down symbol is S, no final states. Now we have to define delta. How do you define delta? Delta of Q epsilon S contains, for the first rule, Q ASB, right. Q epsilon S contains Q ASB, then delta of second rule Q epsilon S contains QAB. So, you can immediately say that it is non-deterministic in nature. You have two moves for this, Q epsilon S either you can replace by ASB or AB, it is non-deterministic. Then A and B are the two terminal symbols. So, delta of QAA contains Q epsilon, delta of QBB contains Q epsilon. Now, let me take an input and see how it works. You know that the grammar generates equal number of A's and B's, or equal number of A's followed by an equal number of B's, that should be the way. A, B, 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 how this will be accepted. This push down automaton should accept that. So, you start from here with initial state is throughout Q, so need not mark that. Initially you have S. Then when you have a non-terminal on the stack, you use an epsilon. When you have a non-terminal on the top, the stack symbols are terminals and non-terminals. So, when you have a non-terminal on the top of the stack, you use an epsilon move. When you have a terminal on the top of the stack, you use a pop move. Okay. So, now you use an epsilon move, this epsilon S will be, you can use the first move, delta of q epsilon S contains q A S B. So, this S will be replaced by A S B, leftmost symbol becomes the top of the stack. Now, you have a terminal symbol on the top of the stack. So, you have to use a pop move. So, this A will be read and this will be removed from the stack. Now, again the top of the stack is a non-terminal, then you use an epsilon move. You can again use the first move. So, it will be A S B on the push down store. Now, the top of the stack is a terminal symbol. So, you use a pop move. So, this will be read and this will be removed. Now, again the top of the push down symbol, top of the stack is a non-terminal. So, you use the second move, use an epsilon move, replace it by AB. Now, the top of the push down stack is a terminal. So, you read this, remove this, read this. Now, again the same thing will happen, read and remove this, read this and remove this, read this and remove this. At the end the stack is empty. Actually, you are simulating a leftmost derivation of the grammar on the stack, but in the case of a linear grammar, this is a linear grammar that does not make a difference between leftmost, rightmost and so on. So, happens that there is only one non-terminal. Generally, a leftmost derivation of the grammar is simulated by the push down automata. So, coming to the proof of it, the PDA simulates a leftmost derivation in G. The PDA M, we have defined it as M, simulates the leftmost derivation in G. This is what we have to prove. So, given a grammar, we have constructed the push down automata. In the proof, what we have to show that if a string is generated by the grammar, it will be accepted by the push down automata. And if a, see, that is what in the proof, what you have to prove is, if W belongs to LG, then W belongs to N of M. One way you have to prove. In another way, you have to prove that W belongs to N of M implies W belongs to L of G. Please note that construction is one way and proof we have to do this. Then similarly, when we construct the grammar from the push down automaton, we have to prove, right. So, first we have to prove this. So, suppose W belongs to LG, then there is a derivation S is equal to gamma 1, gamma, this is a leftmost derivation, gamma n equal to W. This is a leftmost derivation. So, what can you say about each gamma I? Each gamma I will be of the form some xi a some alpha I dash. This xi will be a terminal portion. This is string of terminals. Leftmost non-terminal is always replaced. So, if each one is a sentential form, right, each from S, which is gamma 1, you derive by one step gamma 2, by one step you derive gamma 3 and so on. So, it is a leftmost derivation. So, what can you say if A is the leftmost non-terminal, this portion is a string of terminals, xi belongs to T star, right, and this alpha I dash can be anything. At the next step this A has to be replaced, next step A will be replaced, right. So, what you prove is, if in this derivation you have gamma I like this, from Q W S, this is the initial configuration, isn't it? There is only one state, state does not change throughout. W is the whole input to be read and S is the initially the stack contains only S. And ID of the push down automaton we have earlier seen that the ID consists of 3 components, Q some X alpha or something like that, 3 components. Q is the current state, X is the portion of the input still to be read, and alpha is the content of the stack, and ID is defined like this. So, what you prove is QWS, you can go to Q yi alpha I for all I, you have to prove by induction this step, where what is yi, what is alpha I? W can be written in the form xi yi, W is xi yi, and from going this ID to this ID, this xi has been read. Push down automaton has consumed this input, it has read this portion. This portion which is still to be read is yi. And what is alpha I? Now, gamma I is xi alpha I. Gamma I here is xi alpha I. That is, this terminal portion has been derived and this is still some portion which is to be derived. Please remember that the leftmost symbol of alpha will be really a non-terminal, right. Now, use induction, what do you get? First, when I is equal to 1, what is gamma 1? It is S itself, gamma 1 is S itself. So, what can you say? Gamma 1 is S, so x1 is epsilon, y1 is W, the whole input has to be read now, okay. So, QWS reflexive transitive closure QWS, right. Xi yi is W and gamma I is xi alpha I. What is alpha I? Alpha I is S, right, alpha 1 for that matter. So, basis is okay, induction step. Suppose QWS you can derive Q yi alpha I where you must remember that alpha I, the leftmost symbol is a non-terminal, right. Then to prove QWS derives Q yi plus 1 alpha I plus 1. Now alpha I can write as some A alpha I dash, leftmost symbol is a non-terminal. So from this Q, this we can write as xi yi, xi actually it is like this, xi yi, w is after reading this portion the stack contains alpha I, that is the situation. Alpha I is A alpha I dash, right. I am sorry, this is S. So in you from this you go to Q yi A alpha I dash, alpha I means A alpha I dash. So in this derivation, the grammar, you have gamma I is xi A alpha I dash. The next step, gamma I plus 1, you have x I, A will be replaced by beta, A will be replaced by beta, then this is that, right. Now beta can be fully terminal or portion of it can be non-terminal, portion of it can be terminal and so on. Whatever it is, suppose I assume, I mean this is only one case, beta can be full of terminals also, does not matter. So the thing is, next step A is replaced by beta, then after you replace it you get gamma I plus 1. Now this you can write as xi plus 1 yi plus 1. This you can split so that the first portion is entirely terminal, yi plus 1 may contain some non-terminal and so on, right. So in this step from gamma I you go to gamma I plus 1 in the leftmost derivation. What you do is A is replaced by beta. So you get xi beta alpha I dash. This you can write as xi plus 1 yi plus 1, where xi plus 1 includes xi, I mean prefix of xi plus 1 is xi, and all the terminal portion is there. The first non-terminal is B and whatever is occurring after that is beta. I am sorry, this is not yi plus 1, that is not sorry. Beta alpha I dash, this you can write as xi plus 1 B alpha I plus 1 dash. This is sorry, it is not yi, I made a mistake, this is alpha I plus 1 xi plus 1 alpha I plus 1. This can contain non-terminals, right. W only can be written in the form xi plus 1 yi plus 1. Now what is this yi plus 1? What is this yi plus 1? Okay, I will take a simple case. Where beta has a non-terminal. Okay, that is only one case, other case will be similar. So suppose beta has a non-terminal, beta is beta 1 beta 2, right. The first symbol of beta 2 is a non-terminal, beta 1 is terminal. So when you get xi beta 1 beta 2 alpha I dash, right. The first symbol of this is B and you have something, this you call as alpha I plus 1. This is fully terminal, beta 1 is fully terminal and so that will be xi plus 1. So here what happens is, after this step this yi, the first portion will be beta 1 and so on. It will be like this. The yi, see the portion, this beta 1 you will consume, and so this is xi plus 1 means w is xi plus 1 yi plus 1. What is xi plus 1? Xi with beta 1. So, yi is beta 1 yi plus 1. This is equal to this. Yi is this is equal to this, and a alpha I dash you have. Now, a will be replaced by beta. So, the next step what happens is this beta 1 beta 2 alpha I dash. Now, beta 1 consists of terminals alone. So, you can use moves of the form QAA contains Q epsilon and pop the symbols. So, this will be read and this will be removed. So, you will end up with Q yi plus 1 beta 2 alpha I dash. But what is beta 2 alpha I dash? That is alpha I plus 1. So, that is equal to Q yi plus 1 alpha plus 1. This is a case when beta contains a non-terminal. Beta can be full of terminals also. In that case, you will read symbols up to the first non-terminal in alpha I dash. You will be reading symbols, terminal symbols, and popping off symbols from the stack. So, whatever it is, if you have this, you can have this. By induction, from this step you can go to this step. And generally, in the derivation, from S you go to W. That means the nth step yn is epsilon, alpha n is also epsilon, W is xn yn. So, xn is W, yn is epsilon, and you have gamma n is xn alpha n, xn is W, alpha n is epsilon. So, W. So, xn yn is epsilon, alpha n is epsilon. So, from QWS you go to Q epsilon. What does that mean? You are accepting W by empty store. So, if a string W is generated by the grammar, it is accepted by the machine by empty store. Okay. So, now we have to prove the converse. Converse, not the converse, I mean this portion. If W belongs to n of m, then W belongs to L of Q. How do you prove this? Now, we have to prove something more general. If you have some Q x a, from this state if you go to Q epsilon epsilon, you are starting in state Q and you are consuming the portion x on the input tape. You are initially starting with A on the stack and then ending up consuming the whole input and emptying the stack. In this case, you show that A derives x. From A you can derive x. Okay. This implies A derives X. This portion you have to use induction. To show this you have to use induction. There the induction was on the number of steps in the derivation of the grammar. Here the induction is on the number of steps of the moves of the PDA. Number of moves of the PDA. So, for one step, one move, basis class will be one move. So, from QXA you get Q epsilon epsilon in one move, not no star, in one move you get. What does that mean? See, terminal symbols can be consumed, input can be consumed only when you have a terminal symbol on the stack by our construction. The way we have constructed, when there is a non-terminal on the top of the stack, you can use only the epsilon move. When there is a terminal on the top of the stack, you can use a true input move and consume an input. So, when there is a non-terminal on the top, you can use only epsilon move. That means X is equal to epsilon, right, and you have this must you should have written because of the rule A goes to epsilon. This one is possible only if you have a rule like A goes to epsilon, isn't it? Then only you will remove the stack. Otherwise, A is replaced by beta, beta will be here, isn't it? If A is replaced by beta, you will have beta here. You are having epsilon, that means A goes to epsilon is a rule. That is how you have written this mapping and come to this move, right. So, that means from A you are able to derive epsilon. This is the basis portion, basis class. Now, true for n, true up to n minus 1. So, induction portion true up to n minus 1 moves. Here strong induction we use up to n minus 1 moves we assume, okay, strong induction up to n minus 1 steps, the result is true. From this you go to this in, if you go to this in I steps where I is less than or equal to n minus 1, the result holds. Then you prove for n, okay, prove for n steps. Now, if there is a non-terminal on the stack, top of the stack, then what can be the first move? First move has to be an epsilon move. No input will be consumed, but A will be replaced by something, isn't it? So, in the grammar, if A is replaced by say y1, y2, yk, some set, some string, some of them may be non-terminal, some of them may be terminal. Then you have a mapping delta of q epsilon A contains q y1, y2, yk, isn't it? This is the way we wrote down the mapping. So, A will be replaced by y1, y2, yk on the stack. That is the first step. You would have used an epsilon move, no input has been consumed, but the top in the stack you had A, now you have replaced A by say y1, y2, yk. Stack you have done this, right. Some of them may be non-terminals, some of them may be terminal symbols. The stacks push down symbols consisted of both n and t symbols. Now, what is the input to be read? Input to be read is x, you are reading x, right. After reading x, this stack is empty, that is what it means. After reading x starting with A, the stack is emptied, right. So, after reading this, suppose x is this, some portion. After reading that, the stack is emptied. Now x is split as x1, x2, xk, x1, x2, x3, xk. Now during reading this y1, the stack may grow, and the first time y2 is exposed as the top of the stack, you would have read some portion, and that is x1. Some portion of the input you would have consumed, and that is x1. Now y2 is exposed as the top of the stack, right. Now you read some more portion, and when y3 becomes the, in between the stack may grow and come back, but the first time y2 is exposed as the top of the stack, you would have read x1 and x2, both this portion you would have read, right. Similarly, when y4 is, y3 is consumed and y4 becomes the top of the stack, x3 is the portion of the input you have read, and finally xk is read. What does this mean? It means that starting with q, when you read the xi portion with yi on the top of the stack, at the end, in between it may grow and come back, but at the end yi is removed, the next symbol becomes the top of the stack, but here we are starting with just yi, right. So, this q, the input xi has been consumed, and how many steps it would have taken? This whole thing takes n minus 1 steps. First step is to replace a by this, right. After that it has taken n minus 1 steps to reach this, but this itself would have taken some much less than n minus 1, is not it. So, by the induction hypothesis you have yi derives xi. Right. So, the first step you have replaced a with y1, y2, yk, that could have happened only if you have a rule like this, right. Only if you had a rule like this, you can replace the stack by y1, y2, yk. So, that is from a you are able to derive y1, y2, yk. From yi you can derive xi. So, for each one of this it happens x1, x2, xi, xk, and this is nothing but x. From y1 you can derive x1, from yi you can derive xi, from yk you can derive xk, and so on. So, that is from a you can derive x. So, we have proved this portion using induction. Okay. Now, in the end, what is the initial ID? Q, W, S. This is the initial ID, is not it? This is the initial ID. And what is the final ID? When W is accepted, this is the final ID, is not it? Acceptance by M test. So, use that. If this is possible, that means S derives W in the grammar, is not it? A derives X, here S derives W, right. So, we have proved both this portion. Given a grammar, we have constructed a push down automata. The construction is like this. Given a grammar like this, you construct a push down automaton. The other components I have rubbed off. Delta Q S phi, you have constructed an automaton. The rules are, the mappings are given like this. If A goes to beta is a rule in P, then you have delta Q epsilon A contains Q beta, and for each A in T, each terminal symbol you have delta of QAA contains Q epsilon. This is the construction, and for this construction you have to show LG is equal to NM, and that you show like this. You show that the PDIM simulates the leftmost derivation in the grammar, and in 2 steps you prove that given a W in LG you can show that it can be accepted by M by empty store. Here this portion you prove by induction on the number of steps in the derivation. Okay. Then you also show that if W is accepted by empty store by the push down automaton, then W is generated by the grammar. Here the proof is by induction on the number of moves of the PDA. Okay. So this is one proof. There is another proof where the grammar is in Greibach normal form. Grammar in Greibach normal form. So, G is equal to NTPS in GNF. Now, without loss of generality, you assume that epsilon does not belong to LG, because anything without epsilon can be generated by a grammar in GNF. If epsilon is there, you have to make some adjustment. You have to add S goes to epsilon, make sure that S does not occur as the symbol on the right hand side and so on. So, without loss of generality, you can assume that S epsilon is not in LG. You have to make small modifications if epsilon belongs to LG. Now, how do you construct the push down automaton which accepts by empty store? The construction is slightly different. You have only one state, the terminal symbols are the input symbols, but now the push down symbols are only non-terminals. Terminals will not occur as push down symbols. Delta we have to define, Q is the only state, that will be the initial state, S is the initial push down symbol, all those things are same. Now the delta mappings are similar. If A goes to A alpha is in P, Greibach normal form, you remember that left hand side you have a non-terminal, right hand side you have a terminal symbol, single terminal symbol followed by a string of non-terminals. So, alpha belongs to n star, it can be epsilon also. If it is epsilon, the rule is of the form A goes to A. So, if this is the rule, you have delta of QAA contains Q alpha. Here again we can prove by induction and so on. I will illustrate with an example. Consider this grammar, S goes to ASS, S goes to B. This also will simulate a leftmost derivation. So, you have S goes to ASS, ABS, AB, this S is replaced by ASS, ABA, this is replaced by B, AB, AB, B. Now, how this will be simulated by the automaton, what will be the mapping here? The mappings will be delta of Q A S contains Q S S, delta of Q, for this the mapping is this. For this the mapping is delta of QBS contains Q epsilon. So, let us see how this will be accepted, AB, AB, B. So, all state is always Q and there are no epsilon moves, only true input moves are there. See here always an input is consumed and stack contains only non-terminals. So, you have S on the stack. So, when you see a S with S on, when you see a with S on the top, what happens? S is replaced by SS. The input pointer will now be moved here. Now you see a B with a S on the top. So, what do you do? Pop it, read the symbol, pop it. Now we see a S on the top and you are reading a A. So, what happens? It will be replaced by SS and this input will be consumed. Now, you have a S and a B combination. So, you remove this, again S and a B combination, you remove this, at the end the stack is emptied and so on. This is a DPDA, is not it? This one is a deterministic automaton. So, you see that this proof also you have to formal proof you have to use induction on the number of steps of the in the derivation. Here again leftmost derivation is simulated. Now, I have one question, you can think over this. We have showed the equivalence between acceptance by empty store and acceptance by final state. That construction was very clear. From initial configuration of one you go to the initial configuration and another, simulate and finally either erase or go to a final state, right. Remember the proof? Can you do that for DPDA? We have considered non-deterministic push down automaton and proved that. For deterministic push down automata is acceptance by empty store and acceptance by final state equivalent. Think over this and in the next class you tell me, right. I will give you a hint. Can any regular set be accepted by a DPDA? Huh? Because you have to have the storage, you do not manipulate the push down store at all, but that is by defining a final state, right. Can you accept A star or A power n greater than or equal to 0 or A power n greater than A star, the regular expression A star is A power n greater than or equal to 0. Can you accept A star by a deterministic push down automata by empty store? We can accept it by a deterministic automata, push down automata by final state, definitely. Any regular set we can accept by a DPDA with final state, right. So, think over this. Even simple regular languages like 0 star cannot be accepted by deterministic push down automata by empty store. Suppose we want to accept 0 star by a push down automaton by empty store. If the initial state is q naught and the initial push down symbol is z naught, then to accept epsilon there must be an epsilon move for the q naught z naught combination. Now, to read a you must have a move for q naught a z naught. So, this cannot be empty, you will have a move for q naught a z naught, and to accept epsilon you have a move for q naught epsilon z naught also. So, both of them are not empty. So, q naught epsilon z naught and q naught a naught z naught both are non-empty, and if this happens the machine is non-deterministic. So, we cannot accept 0 star by a deterministic push down automaton by empty store.